Hello and welcome back to the course on statistics. And today we're going to talk about what it means when you cannot reject the null hypothesis. So previously we had the homework about the spoons, about the factory of the spoons where you were working as a consultant. And by the way, if you haven't done that homework, then I highly recommend going back to it before proceeding with this tutorial, because we're going to discuss the result that we got in that homework and how to think about it on an intuitive level. You still definitely can follow along. You'll be able to pick it up from here, even if you haven't done the homework, or even at least watch those tutorials. But I think it will be beneficial if you do. If you have, then let's get straight into it. All right, so that was our challenge over there, and we discussed what we're working with. So that's our null hypothesis, that 18% or more have defects. So just P is greater than or equal to 18%, less than 18%. Alternative hypothesis is that less than 18% have defects, so P is less than 18%. Drew this up, did the calculation, so we know mu P according to central limit theorem is 0.18% plus the new formulas that we learned in the previous section of the course. Sigma is 0.384, calculate sigma P hat is 0.153. And so as you can see, we calculate Z score minus 0.87. So that means here we've got mu P hat, and P hat is sitting only under one standard deviation away from mu P hat. And in terms of our proof, that's actually a bad thing. That means that we will not be able to reject the null hypothesis because, as we know, if you're sitting inside one standard deviation, 68% of observations fall inside the first standard deviation this way and this way, total 68%. And so there's no way you're going to reject a null hypothesis with a 95% of confidence if you're sitting in here. You can do that if you're sitting in the tails, because we know that 95.4% fall into these two standard deviations. That's why standard deviations are so powerful when you draw them. Like, we know that 95.4% observations fall into these two standard deviations, meaning that if you're sitting inside these tails anywhere outside here, and even a little bit inside, like a little tiny bit inside, you can reject the null hypothesis with 95% confidence, because there's only like a 5% chance of being here, and a 95% chance being here. Or there's a 5% chance of being here, well, just here plus a little bit. Actually, not just a tiny bit, but like a little bit more, because you get this tail on this side as well. So you get 95% being here, plus like a little bit from here and here. That's where your 5% confidence sits. It's nowhere near the internal standard deviation. So if you fall inside the internal standard deviation, you are very safe to say that there's no way you're gonna reject something for 95% of confidence. And as we established, P is equal to 19.22%. So there's a 19% chance that to fall inside this huge tail, or it's not even tails, like from here all the way, including the tail. 19.22% chance, much greater than 5%. So definitely we cannot reject a null hypothesis. But at the same time, we cannot reject the alternative hypothesis either. There is simply no such language in statistics as to say we reject the alternative hypothesis. You can reject the null hypothesis because that's your default scenario, that you're saying, okay, if this were true, let's test out, would we come to any contradiction? But if you don't come to a contradiction, then it doesn't mean that this one is incorrect. That just means that maybe you didn't have enough evidence. And that's exactly what we say. We didn't have enough evidence to reject the null hypothesis. A good way to think about it is, imagine that the null hypothesis, let's do an extreme example. The null hypothesis says, if you eat too much ice cream, as much as you want ice cream, then, or let's say if you eat over 100 buckets of ice cream, you will not get sick. You will never get sick. That's the world you live in. And then your alternative hypothesis says, well, actually, probably if you eat a lot of ice cream, you will get sick. If you eat over 100 buckets of ice cream, you will get sick. So it's completely unrelated to what we're doing here, but just as an example. So let's try it out. And then you go and get a sample. So you go and eat over 100 buckets of ice cream and you don't get sick. Does that mean that you can reject the alternative hypothesis? No, it doesn't. Like, if you did get sick, then you can reject the null hypothesis because you have an example of when it's incorrect. This is the law, and you have found an example when the law is incorrect. And therefore, you've completely rejected this law. It has to be rethought completely, like this rule or like law of physics or law of biology that you won't get sick. On the other hand, if you didn't get sick from all that ice cream, it doesn't mean that you can reject this alternative hypothesis. It just means that you have one example of one person who ate all this ice cream and didn't get sick. You need more and more and more examples, and maybe one of them will reject the null hypothesis, but you cannot ever reject the alternative hypothesis. If you want to do that, you have to restate your problem, and you have to do different tests. You have to test this hypothesis, the main one, rather than this one. So going back to what we're saying is that you have the null hypothesis, and you cannot just prove it to be correct. You can prove this one to be correct. You can prove this one to be incorrect. That's what we're doing. We're saying, assuming this is correct, let's come to a contradiction. If we come to a contradiction, this one is incorrect, this one is correct. But if we don't come to a contradiction, then we cannot say that this one is incorrect because we never assumed it was correct in the first place. So that's the thing. We have to keep that in mind, that the only thing we can say here is that there is insufficient evidence for us to reject the null hypothesis. And hopefully that's clear on what exactly is going on here. And this is just a mathematical approach to proving hypotheses or theories and lemmas and so on, that you first assume something is correct and then you try to come to a contradiction. If it's incorrect, if this is incorrect, the only possible alternative has to be correct. It's just logical. So if you assume this is correct, you came to a contradiction, it's incorrect. The only alternative possible is correct by default. On the other hand, if you assume something was correct, you tried to come to a contradiction, but you didn't come to a contradiction. Here, it's totally fine. This is what we're saying. There's no contradiction. It's totally fine for us to have picked a sample. You didn't come to a contradiction, then that means you cannot say that this is incorrect. But also at the same time, it just has nothing to do with the alternative. Alternative just kicks in only when the main one, when H0 is incorrect. But if H0 wasn't, you cannot prove that H0 is incorrect, then there's nothing you can say about the alternative hypothesis. Might be true, might not be true. So let's explore that in a bit more detail. So there we go. That's our two hypotheses. So what's going on here is that we picked a sample. In this world, we said, okay, this is the universe we live in. There is our mean of the proportion that we're testing. We're assuming it's sitting over here at 18%. Let's come to a contradiction and prove that this is incorrect. That if this P was in the tail, we would say that no, it's not sitting here, it's somewhere to the left, and we'd prove exactly what we want. But we couldn't. We didn't come to a contradiction. So P is sitting here. But the thing is that it doesn't necessarily mean that H0 has to be correct. We assumed it was correct and we didn't come to a contradiction, but it doesn't mean it has to be correct. Let me show you why. What if, forget about this blue one, forget about this distribution that we're testing. What if in the real world, not in this H0 hypothesized world, in the actual real world, the distribution looks like this. So mu P star, or this whole green distribution, is what we have in the real world. Could we still pick this sample? Does this sample look like it could have been picked from this green distribution? Yes, it does. It looks like it could have been picked from this distribution because maybe it's sitting at, like this tail, maybe 5% is somewhere over there, and it's sitting around 10%. And that's totally fine. That means it could have totally come from this distribution, no problem. So there's lots of potential distributions that could be the case. So it doesn't necessarily, the fact that we didn't come to a contradiction doesn't mean that this is correct and this is incorrect. No, it just means that in our case, we picked such a sample that totally fits this distribution. But if this is the real case and we go and pick out another sample, get more evidence, then maybe next time we'll pick a sample from here, which will work for the green distribution, but won't work for the blue distribution. And that way, in that case, we will be able to say, okay, the blue distribution doesn't work, and this mu p hat is incorrect, so it has to be more to the left. But for now, the only evidence that we have is not suggesting that that is the case. So that's why we say there is insufficient evidence to reject the null hypothesis. We need to go out and get more evidence. And what do you need to do? Well, you either pick more samples, you maybe increase the sample size. As you remember, increasing the sample size will make these distributions narrower. And so if the green distribution is indeed the true scenario, it'll just become narrower. It'll look like this, like very narrow. And that means you will most likely pick a probability from here closer to here. So making your experiment easier, making it for you easier to reject the blue distribution and just keep the green one. Well, and also maybe the green distribution isn't the case. Maybe something else, maybe the blue distribution is the case, and then you'll get closer to the blue distribution again. Yeah, so the only thing you can do in this way we structure our hypothesis testing is we're assuming H0 is the true universe that we live in, is correct, and we try to come to a contradiction. Only by coming to a contradiction, we can only reject H0. If we don't come to a contradiction, it doesn't mean we can reject H1. It just means that it could be something like this, where we picked a p hat, which, yes, it fits the hypothesized H0 distribution, but it also could be coming from an actual real distribution, which is this green one, and that just means we need more evidence to find out that the blue distribution is incorrect. So there we go. That's how hypothesis testing works on an intuitive level, and what happens when you cannot reject a null hypothesis. You just have to state that, no, we don't have enough evidence to reject a null hypothesis. And maybe you might want to, after a couple of these things, you might want to test the opposite. You might want to do this like as an original scenario, the H0, and then test that. Or maybe you might want to change the value, not 18%, do another different percentage. So you would have to redesign your experiment if this experiment continuously keeps leading to inconclusive results. Then you just redesign your experiment and maybe you prove a weaker hypothesis, or as we said, you do the opposite. So there's lots of things that you can do after that, but this design of the experiment, the only conclusive result that you can hope to get out of it is to reject the null hypothesis and keep the alternative. There's no other conclusive results that you can get from an experiment like this. And while we're here, so hopefully that all makes sense. I know it's a bit still new, but hopefully we'll have some more practice or in the course so that you can get your kind of mind around all of this, how this is working. Okay, so the other thing I wanted to mention while we're here, let's get rid of that green distribution, and let's just hypothesize a little bit more. Let's say we have a green distribution here. The question is, could the distribution, the blue, like we're saying the blue distribution is true, but could the real distribution that's happening in the real world, could it be this green one? Well, as long as we're sitting in the above the 5% part of the tail, yeah, this one could be the true distribution. It totally could be the true distribution, and there's nothing stopping us from saying that could be the case, because as long as we sit inside, as long as we're to the right of the 5% of this tail, this green one, that could be the case. And this distribution could also be the real distribution. So as long as for this distribution, we're sitting to the right, this could be the true distribution as well. So basically you can see that any distribution from here all the way to here could be your true distribution. So it could be this one, 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 it could be any distribution in between here that this p hat actually satisfies. And that's why, by getting more evidence, you might pick a p hat from here, and then you cancel out some distribution. By getting another p hat from here, or by getting from here, you'll kind of, by getting more p hats, more evidence, you will be able to narrow it down. Which distribution is it? Which group of distributions it is. Every time you get more evidence, you will narrow it down more and more. And every time you pick a larger sample, your distributions will become narrower, and therefore your p hats will be more extremely close to the real mu p, whatever it is, whether it's here, here, or here, where the real mu p hat is actually located. And the other thing here I wanted to mention is that if you look at this interval from here to here, as we said, any distribution could be the true distribution in this interval, and that is called the confidence interval. But more on that later, so we're not going to delve into that right now. We'll have separate tutorials about that. Just a quick heads up that is yet to come. So I know this was a tutorial full of information, like all this intuitive information about how to think about the distributions and hypothesis testing. And it's totally fine if it's still a bit fresh in your mind and you need a bit more time to process it. Just when we're doing the next exercise, and this is like quite a practical course, there's lots of exercises, just try to think of these things in those terms. Or even you could go back to a previous exercise and try to think in terms of what are we trying to prove, where are we coming to a contradiction, what are we trying to reject, what's the null hypothesis, what's the alternative hypothesis, what is going on here. It's very helpful to think through these things in terms of null hypothesis, alternative hypothesis, what are we trying to reject, what are the why are we trying to get to a contradiction, things like that, because it will help you just get an intuitive feel for this. It's practically, I think, impossible to develop an intuitive feel for this just through one tutorial. You need to put in practice, and that's why we have so many exercises and homework exercises in this course to really help you develop that hands-on skill and also that intuition for these things. Now make sure to check out these videos on the right or the full course in the description to continue your learning, and I look forward to seeing you there.